Hello, let's take a look at electrochemical cells a little bit. A lot of this will be review from last year, but we have two types of electrochemical cells, a voltaic cell and an electrolytic cell. Voltaic cell is a spontaneous or thermodynamically favorable redox reaction where we are turned chemical energy into electrical energy. So that's what makes it spontaneous, is that we're producing electrical energy. Electrons flow and they can do something. The E value will be positive. We'll talk a little about how to calculate E and what it means in a minute. Electrolytic cell, you have a non-spontaneous redox reaction where the electrons are transferred as a result of the outside energy being added. So what does this mean? This means you're taking electrical energy and converting chemical energy into chemical energy. Or you're using chemical energy to run you're using electrical energy to run a chemical reaction that otherwise would not occur. So you have some type of power source in this, and when you calculate the E value, which we'll talk about again in a minute, it will be negative. For a voltaic cell, your oxidation loss of electrons is going to happen at the anode. The reduction occurs at the cathode. You might remember anoxide cat from last year to help you remember this. Like I said before, it's a chemical to electrical energy conversion. It's a spontaneous redox reaction. We'll take a look at what this salt bridge does. So here's a picture, right? So in a minute, we'll see one that has the two half reactions, but you have your oxidation occurring at your anode. You have your reduction occurring at your cathode. You have the electrons flowing from the anode to the cathode measured by the electron flow here. This picture, this helps us visualize it a little bit more. So what do we have? We have the piece of zinc here turning into zinc ions. Now, when that happens, that disrupts the flow of charge. So you're producing two electrons. The electrons can zip on through this wire over to here, but you would otherwise be accumulating positive charge in this half cell here, which is not allowed. So what you have is you have this salt bridge, which is a porous material. It's usually composed of sodium nitrate dissolved in water and then in some type of gel so that it stays in place. But the nitrate ions can come out here and can help to balance this positive charge that's being produced. And a similar thing is happening over here where copper ions are becoming copper. Here you are using up positive charge, so the sodium ions can come out of the salt bridge here to help replenish the positive charge that is getting used up. Similarly, another way to perhaps think about it, this would be like a copper nitrate solution to start with, because you'd always have to have a balance of charge to start with, and the nitrate ion can kind of migrate through, leave here, and go down to here. So either of those are these little pictures kind of visualize what's happening. Yes, you're actually making a coating of copper on this piece of metal, and you're actually eating away at this piece of metal here, according to this half reaction. And this occurs as soon as you attach this, and if you attach a voltmeter in here, you would get 1.10 volts, which we call the E value for this reaction. We'll calculate those in a minute, but that would be what would show up on that voltmeter there. So what is this E? This E is called electromotive force, which is a voltage, right? You can think of a voltage as the driving force, right? If electricity is the flow of electrons, you can think about like the flow of water, right? So in a waterfall, the height of the waterfall, or the difference in the heights between the 2 points of the river, for example, describes the driving force behind the water, right? What causes it to flow in a certain direction. The bigger that height, the bigger the voltage in our analogy. What about the current is the other main thing we talk about in a circuit. In the current, current is the flow of the electrons, right? So how many electrons pass a given point, so like the speed of water. We'll talk about that a little bit more when we're back in person, but that would be the current, is how fast kind of the water is moving, or how fast the electrons move between a point. So we're going to talk about every every redox reaction having this voltage or EMF or this cell potential, and it's measured in volts, and a volt is a joule. Now, how do we get the E for an overall reaction? Well, we need to consider the E value for each half reaction. So we have a bunch of standard reduction potentials listed in the table on the AP exam. They're given to you up on the top of the question. Usually they give you 3 of them, and you only need 2 of the 3 to do the calculation, and you have to figure out which ones. So here's a bunch of standard reduction potentials. So they're always written for reduction. If you want the flip, right, if I wanted to go from 2 fluoride ions to fluorine plus 2 electrons, I would just flip the sign, and it would be negative 2.87 volts. Remember, for an overall reaction, you always have to have 2 half reactions. So when we're calculating an E value, it's most likely one of them is read directly off of the provided information, and the other one is flipped from the provided information. So if you look at this example down here, right, calculate E for iron 2 plus zinc, giving you zinc 2 plus iron. You would find each half reaction, and so this one's directly up above here. This one is in reverse of what's here, so you flip it. Okay. One thing of note, we don't see it in this example, but the stoichiometry does not change the potential. Okay, so if I had coefficients on any of these irons, or it was like half or double, you still use the same E value. That's different than delta H, right? And that is because voltages are an intensive property and do not depend on the amount. So no multiplying by coefficients, but you do flip the sign, similar to how you do in a delta H type problem. So then you just add these 2 up, and the E standard, you use a little degree symbol, which I didn't put in here, would be 0.32 volts for this particular reaction. The higher that value, the more positive it is, I should say, the more thermodynamically favorable it is. If it's less than 0, it's non-thermodynamically favorable. So these are all considered the standard cell potentials. Here's another one you can do. I didn't solve this one out, but you can use that information from the previous page. To do that, you would have F, I'll do it real quick just verbally here. You would have Fe going to Fe2 plus, so that would be the reverse of that. So 0.44 would be your iron half reaction, and then you have Al3 plus electrons going to aluminum, and that would be just written right off here, negative 1.66, 0.44, which was the flip first one, plus negative 1.66, so negative 1.22 would be your E degree. Again, that degree just means you're under standard conditions. The more positive the value, the greater the tendency of reduction. We'll talk about that a little bit. And strongest oxides have the most positive reduction. This is kind of related to that idea. Used as the oxidizing agent. In other words, a strong oxidizer has a positive reduction potential. A strong reducer has a very negative reduction. So we can relate all of this. The last little thing we're going to do here, and we're going to start it here and then finish it up in class. Delta G is equal to negative NFE. This is another equation off the table. Delta G, we know, is the free energy, so it would be measured in joules or kilojoules. N is going to be a little bit tricky, but try not to make it too tricky. It's the moles of electrons transferred in the overall balanced reaction. So if I go over to here, right, the N here would be 2, because this is balanced the way it is, and the N would be 2. In this one, right, I would have to balance this. When I ended up balancing this, I would need 6 electrons. So N would be 6. That's how you get your number of electrons. F is going to be a constant. It's on your tables. It's 96,485 coulombs per mole of electrons. We'll also use that in some future calculations, that value. And then E is your voltage. And remember, a volt is a joule per coulomb. That's how your units all work out. So if you have delta G, in kilojoules, you do have to go back and change that to joules. So we can also relate this to the equilibrium constant, right? And this triangle kind of shows how everything is related. So I just gave you this equation, right? Our next equation here is going to be delta G is negative RT ln of K, right? Which can also be used. Actually, we saw that one a little bit before. So we could also set negative NFE, equal to negative RT ln of K. So a lot of the redox stuff is going to be just kind of, like I said, kind of finding the right equation and solving that out. This equation here is a value calculating E, right? This is, again, if you think about this, you could solve this out, right? When you set two equal to each other and solve them for E, you can get this, and then this lets you go between. So what I have here are a couple examples. So what you want to do, I want you to calculate this kind of on your own. I'm going to put these answers up at the start of our next class. So you're going to calculate E, divide this into its two half fractions, use those two tables on the previous slides. Then you can calculate delta G from that using NFE. And then also you can calculate K using negative RT ln of K. And then here, you can use a little more space. And then here, what if this reaction was silver plus 1/2 of O2? So now think about how this would change N. And again, I'll put that answer up next time. So you can either pause and do that now or do that when I'm done. I'm going to go through just one more thing here. So the last thing we're going to do here is we're going to kind of tie this together. Now, one thing that I've kind of been noting is we have to always kind of be thinking about if we're calculating E at standard conditions, delta G at standard conditions, or not, right? So what this chart kind of does is this says, okay, if I have a reaction under any conditions, if delta G is negative, whether they're standard or not, delta G has to be, if it's negative, the E is positive, right? And the K, if we're not at equilibrium, K is going to be greater than Q here, and that means we're thermodynamically favorable, right? If delta G is positive, E is going to be negative, less than Q, which means we're not thermodynamically favorable. And delta G is 0 under whatever conditions we're at, right? Probably not standard conditions, but if delta G is at 0, or I guess it could be under any conditions. Really. If delta G is 0, the E is going to be 0, and the equilibrium constant is equal to your current conditions, and that's kind of an indication you're at equilibrium. I know I kind of went through this quick. I haven't seen a ton of this. More common, what are the things I really want you to focus on being able to do before we resume? Make sure you can calculate E because we won't have a ton of time to do that. Make sure you're familiar with these equations and solve some simple problems like the two here. And then what we'll talk about tomorrow, we'll just talk a little about this Nernst equation, which isn't really a ton on the AP exam. First form sometimes is, but the second one isn't. In class, and then we're going to talk a little bit about how we can calculate the number of electrons that move or the related all to the current that moves. So that's what we'll work through tomorrow after the